Okay, great. We're back again with Bayesian Statistics. I want to make an announcement real quick that I'm extending the homework until Monday. It's usually my goal to get you started on it and give you 2 weekends, but this one's a touch long and we're still going through some of the materials right now. I also want to give you the extension so it gives you a little bit more time to turn in physical copies. So if you can bring them to class, I really like that. Just saves us a lot of time. So I know it takes you guys a couple minutes to do, but it takes us, if we have to print them all out, like we're sitting there for hours doing all this. So I really appreciate it if you can drop them off if you're attending virtually. Sliding them under my door, it touches and works. So no FERPA violation there because it's my locked office. So that's 401A Hutchinson, it's on the web page. The department is open. So you can just walk in and it's virtually empty. So it should be a safe environment for you to walk into for a minute. If you have friends, you can have your friend turn it in as well. If you have a health issue or some real issue, you don't need to message me explaining it. I trust you. You can email those to both me and Sierra. So, and then we will accommodate you, but we're just hooking up. Hope that makes sense. Okay, so homework extension. I've rewritten the notes for us, so both copies will be uploaded to Slack for your viewing. So I try to clean them up a little bit. I do it for my own good as well. So this is what we covered last time. Our same example, one data point from a normal, our likelihood was that. Which likelihood is that? Well, it depends on which parameters we're estimating. So it could be the likelihood for mu if we fix phi in that equation. It could be the joint likelihood for mu and phi. So I was unspecific here. From this same function, when we held phi as constant, right here we were able to work out the full conditional for mu. And that kind of has a nice weighted average form in the expectation. I kind of like that formula. A lot to think about there. We also discussed taking the conjugate limit and what that converges to. So the classicist would operate off of this distribution right here if you just counted on x. And so our inferences are starting to collide in some sense. Of course, the Bayesian interprets that distribution as a distribution over mu. So the probability of mu in a non-Bayesian does not have the same interpretation for this same thing. We'll be comparing that as we go into decision theory and other aspects of the analysis. But I like to make mental notes as I go there's some similarity here to things that we already know. We also worked out the full conditional for phi, and that turned out to be a gamma distribution. We used the conjugate form, and then under the conjugate limit, we were able to work out that prior right there. So just as a heads up, the implied prior in the conjugate limit on mu is flat, and the implied prior on phi was 1 over phi. We also talked about transformations of all of this. So this prior distribution is improper, just like the distribution on mu, and in some sense, that might be good for us because we're not putting too much weight in certain parts of space, unintentionally. We'll be coming back around to these priors. I'll point out, Laplace used this prior, and I was baffled when I learned that, used that prior as well. So Laplace also used this prior a long time ago, and I was interested in that, and I wanted to know how we thought of where did he come up with it to use it, and I'm not sure the answer to that. So what he was looking at. But he has some idea about scale invariance. He didn't operate on the precision parameter, he operated off of the standard error, standard deviation. You can think about it in terms of variance. So this prior is equivalent to that when we just do our transformation. So all transforms look like this, where you take the base distribution, you plug in the inverse function, and you take the derivative of that inverse function, you multiply those two things together. Make sure it's all positive, the absolute value at the end of the day. This part's always going to be positive because it's a density function in the first place. You'll notice that this is improper, and the implied prior on B is also improper. We didn't show this, but this is the exact same calculation. So when we talked about scale location families, you are familiar with this factor that popped out. That was the Jacobian term. So if you transformed everything to phi, you would be taking your distribution and multiplying it by this. You did it for this right here. So this is the scale invariant term. So scale invariance always means that you multiply by 1 over that scaling factor. However you think about it. What's kind of cool, if you're dealing with variance, it's 1 over variance. If you're dealing with precision, it's 1 over precision. If you're dealing with sigma, it's 1 over sigma is the scaling factor. Those are all equivalent to each other because they're all one-to-one transformations to each other. Just keep in mind, transform is this right here. That's the relationship between everything. So work on your transformations, think about those. There's a good problem on the whole. And it discusses everything in terms of that Bernoulli application we were thinking about. Okay, so if I have a probability P in a model and I want to put a prior on it, it matters how I think about that. So early on, we thought about putting a flat prior on P itself. And this problem that I'm asking you says, think about that, what that means in terms of the log odds. Prior for the log odds is certainly not flat anymore. And then I ask you to do it in the other direction. Put a flat prior on log odds and see what the implied prior on P is. So it's a good thing to think about. And so is your transform, is your parameterization of the model arbitrary? And if the answer is yes, and you just start throwing flat prior on there, it's going to make a difference in your inference. Saying that, if it's a rather diffuse sort of specification, and you have a lot of data, that influence might wear off quickly. We'll be coming back around to these priors because we talked about it semi-conceptually, limits of conjugates, but these are also in one dimension optimal frequencies. And so we'll talk about what that means. I mean, in terms of coverage of intervals. So we should probably have a discussion about that. There is no class of prior that is just optimal frequencies, but there's priors that happen to be optimal frequencies, and that usually takes a whole paper to prove it itself. So the beta half is also optimal frequencies for building intervals for T. Getting to that. Go on.
So under prior assumptions, it's not necessary to have the optimal frequencies properly if you just replicate your priors.
Yeah, I wish it were that easy. So it doesn't work out that way. It's much more complicated. I think people have tried to attempt to do this, and they usually have some computational method that reshapes the intervals and gets it tuned in a simulation study. So I wish that you could have all properties from priors simultaneously, but generally you have to choose. Saying that in one-dimensional inferences, so before the joint inference, we were doing this all one-dimensionally. It's true what I'm saying is moving to 2 dimensions is not true anymore. And so you're not covering the joint step optimally. Now, I don't know any classicist that gives me joint intervals that are optimal frequencies. They usually have an asymptotic property. And so we'll be talking more about that, but what I have kind of said is this is at least a decent prior to think about. So there are some things in some dimensions that you get, and as we move up the dimensionality of the problem, you have to be more thoughtful. So that problem is telling you it matters which parameterization you're working in. Okay. So this was supposed to give us some familiarity with things and understand a little bit of what scale invariance means. Turns out there is a formula that I can use to derive these priors. So when we get to Jeffrey's priors, these are all Jeffrey's as well. And that one a lot of people like because it's just a calculus problem solved real quickly. In one dimension, you can usually solve it. In high D, you might have to write a PhD thesis to figure out what all it is. So it depends on the complexity of the problem. We'll be getting to that. We moved on to the joint analysis of mu and phi. And so same thing that I wrote down for the likelihood function in both problems leading up to this, but now I'm thinking about this jointly. I'm going to use our same priors. I thought these were at least pretty good priors for a one-dimensional analysis. I will point out, most people will use these. Most people will use. Not everybody. There's reasons why you might want to encode information or do something with that. If somebody walked into my office with a couple data points, didn't tell me anything, I'd be inclined to do that. Saying that, I usually don't work on problems where I can just do that. So I usually work on problems that I have to do something more interesting. So, because I want to write a paper about it. If you're just an application specialist, you probably use those. We'll be coming back around to these over and over again. We ended up asking the question, what is the marginal distribution for mu? So this is just averaging right here. We're just averaging over phi, or you can call it marginalizing. And we worked out what that integral was. So we ended up writing it all down up to proportionality. So I should write right here that this is proportional instead of the equal sign. So I haven't normalized everything inside of the integrator. So proportional. And I don't want to do integration by parts to figure this out, but that would be the method I would use if I were back in calculus class. I ended up using the fact that I know that this right here is the kernel of a gamma distribution, and if I had multiplied by the inverse of this thing right out inside of the integrator, that whole thing would integrate to 1. So that's equivalent to saying that the kernel integrates to the inverse of the normalizing constant. And so recognition of kernels, knowing your integrating constants is the key to doing this integral in 10 seconds. So you might feel gypped that we didn't do parts on all of this. So I'll say knock yourself out and go ahead and do it at home. You'll come up with this same answer and you'll figure out right in the middle, you need to figure out this non-closed form expression right here. It's another integral, that's the gamma function. So alpha is not an integer. This is all really expressed in terms of an operator. The nice thing is that this part of it, gamma to the alpha tilde, where alpha tilde is 1/2, where do I look for it? I look in this term. That's where the alpha thing is sitting. Where's the beta thing? It's over here, multiplying the minus phi, that random variable. That's beta, so x minus mu squared over 2. Key point is to recognize gamma distributions, and this problem is easy. If you didn't know anything about gamma distributions and you gave this to, let's say, a physicist, relatively smart person who can integrate, probably knows how to integrate better than us, this would be a little bit trickier. So once you understand what these distributions are and they integrate to 1, it's very easy to do these intervals. So we're shortcutting it. We concluded here by writing all this down. And so I worked out everything last time, and our final answer was this. So I just took beta tilde, raised it to the minus alpha tilde. That's this expression, and then I simplify it in here. This is minus, and the minus sign right there. That's upside down. So I forgot my minus. That's where that comes from. Squaring something, taking the half power of it, that's the absolute value operation. I can get rid of the 2, square root of 2, because I've written down proportionality. And I noticed that you cannot normalize that distribution. It's improper. And so that's of no value to us. Other than insights that says these priors that we use to do the analysis, they're pretty non-informative. They're not centering the distribution anywhere. What you could do to inform the analysis is I could cut a little bit of weight on a mu naught. So I could go back to the conjugate form and not use the limit, and it would turn out that everything was this problem. I said that if you make the priors proper, the posterior will be proper. That's almost true. So I'll talk about it through the math, and we'll see our one mathematical little copy in all of this. If you use proper priors, you're going to inform the analysis. Those are called subjective priors. You're going to be centering them somewhere, putting enough mass somewhere that they integrate through. Our posterior will be proper as well. That seems really great. Without any knowledge about this problem, we really don't have any right to do that. So we're just arbitrarily anchoring the distribution, and maybe that's not a good idea. So I like this answer in terms of insight that says, maybe there's not enough information in the data as well to estimate these two parameters, phi and mu, and that's of course true. So I give you one data point and I ask you for the variance and the mean. You gotta give me a second data point. So second data point is really informative. And a third data point is extremely informative. So I think of that as like infinitely more data. I really like the third data point. I think I would do inference on 3 data points minimally. So somebody forced me into it. Definitely not one in this problem. So I at least like this insight. Let me just tell you a theorem. If your prior is proper, let me just make this a little bit general and say our prior is pi phi. So we'll go back to our default notation of phi being our parameter sense. Phi could be high dimensional, it can represent whatever you want. I've got a prior. So I'm going to say it's proper. So what I mean by proper is that this thing right here, d phi, is equal to 1. That I can integrate it over the whole space of first theta. I said phi, I meant theta. They don't need to be normalized, so a lot of times you'll see people write down that this thing is less than infinity. So that's a more technical, nuanced way of writing that you can use any weighting function. It doesn't need to be normalized. You could normalize it. So we'll just assume our thing is normalized. So it's less than infinity. If it blows up, that's improper. And so our posterior distribution is going to be likelihood. And I'll put in a bunch of data in there, times our prior. So that's our posterior. Proportional to that. Usually I just work with that. And so I want to show that the posterior is proper, i.e. it's normalizable. So if I integrate this, it's going to be equal to 1. Or it's going to be less than infinity if I haven't normalized everything yet. Okay. So they're true. So this is just proportional to the likelihood function. Integral of the likelihood function times our prior. E theta. So here's what I'm going to assume. So my theorem's an almost theorem. That this is a bounded function, the likelihood function. There are cases where your likelihood can fly up towards infinity. I can construct a likelihood function that behaves really badly near a boundary. And so, for instance, something like a Poisson distribution, where I only have one observation and the observation is just 0. And I'm going to start to try to estimate things with that. The likelihood doesn't behave well. And so, that's a bit of a problem. So let me just finish my statement. If your prior is proper, then your posterior is proper. So, and this is an almost. Put in a caveat right here. Almost always true. This has to do with this thing being bounded right here. So if your likelihood function is bounded, what that means is the MLE exists. So if the MLE doesn't exist, you're out of luck in a lot of paradigms. Okay, your MLE is just shooting off to something. It's like, how do I deal with likelihood ratios? So there's a few funny examples that you'll see in Casella and Berger where this happens. So usually what people will say right here is under regularity conditions. And they'll enumerate 17 conditions so that the dominated convergence theorem holds. If you take measure theory, that sounds familiar. I mean, you can bound everything in the maximum doesn't fly off towards infinity. So I'll use the same caveat that everybody else uses and says under basic regularity conditions. What I'm really saying is that the max likelihood exists. So if that's true, then this thing is going to be less than integral L hat times pi theta, E theta. L hat is going to be our max. So I was able to bound everything by plugging in the max of that function. And so you can see in the line where I'm using my assumption, the regularity conditions, that L hat doesn't blow up. Obviously, I can pull this thing out of the equation. And then I'm just left with integrating pi theta, and my prior is proper. So this thing is going to be bounded. Voila. So almost intuitive, same thing as in everything. If your likelihood functions are not behaving well, you're going to be in trouble. There are classes of semi-parametric priors that people will use, and if not well stated, all kinds of problems can happen right here, and you can fool yourself. Percy Diaconis has written a few papers on that if you misspecify your Bayesian semi-parametric priors in certain settings, you can have problems with the likelihood function in general. All kinds of weird stuff can happen. So saying that, I try not to do those things that can be misleading. So a little bit of a theme. So I wouldn't say, I don't think that the answer right here is go make your priors proper, because it'll make your posterior proper. We certainly need that. But you're having more influence than the data points when you do that, especially with just one data point. So the real prescription is go get more data. So let's get more data. So now I'm going to have xi's coming from a normal distribution, and there's two parameters here that I want to estimate. Mu. We'll let I goes from 1 to n. I like to work it out as n. Then I get to see how this behaves as a function of n. This is really useful. Algebra works out really nicely when you scale up the dimensions and you see in the closed form solution n where it floats around. In matrix dimension, matrices are harder to work with. And so in those cases, when I'm really confused, I move to a 2x2, and I work it all out by hand. So as we go through the linear algebra in this class, work out 2x2s, look at what the functions are, and become familiar with what they're saying. Algebraically, when you have these nice little closed form solutions that have been really nice. So our likelihood function is the exact same thing as before, but now I have a product. I'm going to be thinking about this jointly. So I'll write down everything like this, where x right here is just x1 and xn. My likelihood function will be proportional to the product. I goes from 1 to n. And this is the case because everything is IID in my example. So I can state it. You can write it down. And this is just going to look like this. instead of writing sigma down here, this is equivalent to a phi 1/2 on top. E to the minus e over 2 xi minus p squared. That's my likelihood function. Again, when you're figuring out your likelihood functions, you look at the sampling mechanism. How did you sample it? So Bayesians are always interested in the forward process. Tell me the process. They speak like that because they're going to write down their likelihoods for it. You have to think about exactly how the data was generated, and then that tells them exactly how to form the likelihood function. In this case, it's really easy. We'll have more sophisticated problems, non-IID stuff, so on and so forth. Our priors, same priors. We don't want to change that. This is our prior thought on everything. So more data shouldn't change that. So usually if you're thinking about these functions with the data, you're making a critical mistake. There's a couple disclaimers in there. Empirical Bayesians calibrate through the data. There are some priors that do that. We'll get to that later. But just as a stepping stone, if we use our data to calibrate our priors, we're making mistakes. We need to be more thoughtful about it. Okay, so our posterior distribution. Is going to be proportional to, and I'll just simplify this out a little bit. This is going to get rid of this. This is going to be e the n over 2. It's getting product the n times e to the minus e over 2, and I'm going to drag this sum in here. I goes from 1 to n, xi minus mu squared. Sum of squares, pairs. So our favorite friend. See this in all statistics classes, that function pop up right there. And then I've got my priors to work around. And so multiplying by 1 doesn't do too much. And I'm just going to be nice to myself and just throw down my prior right there. So I have a p inverse term, and I'm just going to add that on right there. I always keep that minus inverse there because I know what gamuts look like. So I don't absorb it in. I always just leave it. Very conveniently, the prior just applies it. So that's our posterior distribution. What distribution is this in terms of mu and phi? Kind of an interesting question. On homework 2, I'm going to ask you to do something. It's a new problem for me. I haven't asked this before, but I want you to plot. So contours of this. You can make a 3-dimensional plot. I never know what to do with them. On a piece of paper, a 3D plot. I really like them on a computer when I can rotate them and look at them. I think that's rad. So when somebody shows me a 3D thing, they're just showing off that they can build a nice mesh. It does look cool. So surface plots like that. I like the contour plot for this. So just 2-dimension, and there's density of lines that show where everything is. And so I'm going to ask you to plot the contour plot for pi mu and phi. It's fun to think about what this thing looks like. So you might ask yourself, is this proper? Well, if n is 1, no, it's not. But if n is 2, things start to work out for us. We'll see that in a moment. We'll figure out what this distribution is. At least marginal in a second. But I want you to think about this. It ends up looking really interesting. So I'll just say as a function of phi and mu, this looks a bit like this. Triangular. And this is a function of n. So this is really a function of n and phi in a lot of ways. So phi varies also as a function of mu. So there's three things going on right here. And as n starts to get bigger and bigger and bigger, this looks rounder and rounder and rounder. But at the very beginning, let's say n was 10, it looks very triangular. So if you think about this, you can say there's an association between mu and phi right here. So mu and phi have a joint relationship. Here's a critical error. You can go fix all these papers up for people. Make a whole career on this. People have already started on this. So, low-hanging fruit. If you knew this 25 years ago, your name would be well in heaven. But for things like control chart, quality control process, a lot of things that people will monitor stuff like mu and sigma in the whole process. They want to see that their measurements are staying about the same, and the variance in the process when they're manufacturing something stays about the same. When those jump out of their limits, they say, stop the process, and let's go analyze all those. You hope they do that. I think what they say is how much will it cost if we just ship it all out. Hopefully we're right. One company I'm always very impressed with, I've never had a bike by these guys, but Kawasaki. So Kawasaki is really cool. As soon as one thing goes wrong, somebody pulls the lever and the whole factory shuts down. And everybody meets in the middle and they have a discussion. And so it's pretty cool. So the Japanese are probably the greatest in real quality control that we know. So at least maybe that's my opinion right now. Maybe that will change in time. What people will do is they'll monitor x bar and s squared a lot of times when they're thinking about control charts. And there's something they know about x bar and s squared is they're independent of each other. So as test statistics, that is true. And so they go and they say, let's do the analysis independently. And so they're not monitoring some joint statistic. And so you can improve on all of their results by at least 1%. For some n, this is true, if you take into account the joint relationship. And so you can improve results with this. So depending on what you think this is, your intervals are going to change. Now, a lot of classicists will probably come back and argue, as n gets bigger and bigger and bigger, you lose your advantage. And that's true. So this will start to turn into a circle. Anyway, something to think about. So let's think a little bit more about this distribution. Let's go back to our marginal form. And let's look at find u, given x. So I want to marginalize out everything again. So we want to find this. This is going to be proportional to that function that we just wrote down. I think we can keep it in our minds. Phi to the n over 2 minus 1 e to the minus phi, sum of the xi's minus mu squared divided by 2. I'll drop, I'm going to keep it. I goes from 1 to 2. So where do we integrate from? The average over the entirety of phi space. And this tells us how to average everything and marginalize it out. And so what is this thing? Well, this is going to be gamma, the alpha tilde, over beta, the alpha tilde. So same exact thing. This looks like a gamma with two parameters, alpha tilde and beta tilde. And the whole trick is to recognize what those parameters are. So where do we look for alpha tilde? Right here. That's where it shows up. In front of the minus 1. So that's n over 2. What's beta tilde? We look right over here for it. So that's going to be sum of the xi's minus mu squared over 2. So this thing is gamma to the n over 2. This is going to be sum. I goes from 1 to n, xi minus minus mu squared over 2 raised the n over 2. And those of you that are good at asymptotics just recognize, oh, if n is 2 right here, then everything works out real nice. So this is going to be integrable. We're going to be able to integrate out this whole function. If you haven't seen it yet, you'll see it in a moment. Keep in mind, this is just a number. As soon as we wrote down this proportionality sign, all of our little constants don't mean anything. If we want to normalize it, we're going to have to do all the same work at the end, so just keep tossing things. This also can be tossed to 2. So this looks like this. Sum of the xi's minus mu squared, I goes from 1 to n, to minus n over 2. Who recognizes that distribution? So this is the whole Bayesian game that we're trying to get you to recognize. What is that? And so if you're really sharp at this, or if you've done the problem before, you know what distribution that looks like. Now keep in mind it's just a kernel of the distribution. We've lost all the normalizing constants. So what is that thing? And just to see if you're paying attention, I told you last time. So the answer hasn't changed. It's a t. So, but we need to recognize that. And that's not so obvious. And which t is it? So this is a t. Some t distribution that we need to recognize. T distributions have 3 parameters. And we need to know what those parameters are and where they show up in this function. So, 3 parameters. I'm going to write them down like this, fairly arbitrarily. You know, I'm going to just switch the paper and do an aside moment. So I think it's fair to talk about this distribution. I'm going to try to recycle some of the notation right here. So let's just do an aside and talk about what t's look like. So t distributions. So aside. So we're going to have a quick breakout discussion to discuss t's. In all my notation, it's not exactly supposed to match what we just saw in the other problem. So z is going to be our random variable. I'll try to do it like this every time when I do an aside on a distribution and use a different characterizing random variable. T. I'll tell you what the PDF in a second is, but I want to use our old friends to characterize this distribution. This is going to be the location parameter. So in the problem, we are just discussing mu as our random variable. Now in this problem, mu is the location parameter for z. Okay? They do have something very in common with each other. There's a scale parameter. And there's a degrees of freedom. If you weren't in a fraternity growing up, I was not, so I never knew what all these terms were. I just had to see enough math classes until they recycled enough letters before I learned the Greek alphabet. Still probably am missing some of it. This is called mu. It looks like a V. A lot of people would use that. Okay. This looks like this. PZ. This is our density function. If you like the notation we've been using, usually I would condition on all of these parameters. So sometimes I'll write that stuff in. Bayesian textbooks are inclined to do this because you know what they're going to do with those parameters. They're going to multiply prior into an operator on being positive. Do the Bayes theorem. So this looks like this. There's a few normalizing constants in here. I have to write them down because I never remember what they are. But I'll say there's normalizing constant stuff. We'll write it down in a second. The important stuff is right here in the kernel. That's what I'm always inclined to know. Because I don't know the normalizer, probably means I never use it for anything. And it's true. I've never used it in my life. So you would have to use it if you're doing like a T predictor. Something like that. I've never done that. Exactly. So the important bit looks like this. X, or sorry, this is Z, minus mu squared. This is over mu sigma squared, the scaling parameter. And this is going to be raised to the minus mu plus 1 over 2. If you're used to taking limits as functions of mu, this looks real familiar to you. So if you take a limit as a function of mu, that thing, it turns into a scaled version of e raised to this junk over here. So t's limit to normals is what I'm saying. So kind of fun to think about. Okay, here's the bit. This is gamma function mu plus 1 over 2 square root mu pi. And there's another gamma function mu over 2. And then there's our old friend, the scaling parameter that pops out in front. If you go to Wiki, they don't have the scale parameter written down and all of that. But from what I told you from scale transformations, you could have plugged it in and knew that that thing shows up right here. If you want to head start looking at the multivariate form of this. I had you look at the multivariate form of the normal on your homework. So we're going to be building all this up in higher dimensions. That's a t-distribution. And every Bayesian I know knows this part of it off the top of their head. Boom. I remember when I was taking one of my first probability classes, and there was something, or some Stat 101-esque class, and I asked about t-distributions, and I'm like, what does the density function look like for this thing? I've never seen it in any of these books that I have. And I was being taught by non-Bayesians, and they didn't know off the top of them. I'm not going to look at it for a while. There's some table over here. Nowadays, we have Wikipedia, we can look it up. We need to take what we just solved and make it look like this. We need to recognize sum I goes from 1 to n at psi minus mu squared to the minus n over 2 as star. So we need to compress it into that form. It's not too hard. So what I'm going to do is just what I know how to do. Expand this out, see what the terms look like. So we might not be able to finish this completely, and we'll come back to it next time. But this is, again, just to remind you what this is. This is our answer, our posterior distribution. So in my class, if I ask you on a test for a distribution, it's not good enough to write a proportionality sign and say, here's something, and you figure out the rest of it. You need to tell me what the distribution is and how it's parameterized. So when I ask you for a distribution, that's what I mean. So give it to me in a form where I can understand it real quick. If somebody shows that to me, the only reason I know what it is because I know what the answer is. So I've done it 14 times. This is the 14th time I've taught this class. So what we're going to do is just expand. So no secrets right here. So So this is just going to be sum I goes from 1 to n. And I've got this square term right here. So these are the xi squared minus 2 mu xi plus mu squared. Close that brace. Now I'm going to expand everything. So this is just going to be sum of the xi squares minus 2 mu sum of the xi plus n mu squared. No indexing there. So I just have everything going through. My sum is specific now to the terms they're sitting right in front of them. I always hate that when I'm looking at folks and I can't tell, does your sum drag all the way through? We have to like figure it out. So I do like when people have little braces, but maybe that's too much for this. This I can recognize is something. This is going to look like n x bar. This is just constant. You can't exactly just factorize that thing out. I can't just get rid of it. I want this thing to look like this, right here. And so I need to start thinking about what this distribution really is, other than this form. We have 2 minutes left. The algebra is about to get tricky. But what I'm going to do is I'm going to try to get this 1 to appear, right here. So I'm going to take everything and divide it by this term. I'm going to start to recognize what all these little factors are right here. So you might even recognize what this has to do with s squared, stuff like that. So I want to come back and rewrite this. But the answer is going to look like this. Eventually, after we finish this algebra, you'll get plenty of experience with this. This is going to be a T distribution. This has a centering parameter, mu, a location. What do you think it is? It's x bar. Great intuition. So, what do you think the scale parameter is? It's kind of giving you a hint. Yeah, exactly. It's s cap. So this is sum of squares thing. So sum of the xi's minus x bar squared over that. So when we divide by n, we're going to have an n minus 1 that appears as well. That shows up right here as the degrees of freedom. And so this will match your intuition. So once we do all of our algebra, we'll get that distribution right here. So that distribution, oh, this is n minus 1 here. I apologize. That gives it a minus 1. That distribution is what a non-Bayesian would use to do inference in this problem. And so we see another sort of collision between Bayesians and non-Bayesians using the same distribution. We're going to derive it for you here, and that's just what you get. Where in a lot of your classes, at least as an undergrad, they just kind of told you, and maybe they worked out, if I take the x bar and I divide it by the sum of squares, and I divide by the degrees of freedom, you may have worked out that that has a t distribution. Or that has a chi-squared distribution. If you divide all that into the shifted normal thing, that's t. I should probably write down all of that. So a lot of ways to recognize